Hello students, and welcome to section 8-1, Key Features of a Quadratic Function. So we already are familiar with parabolas. A parabola is a graph of a quadratic function. In example 1, we're going to start off by identifying a quadratic parent function. What is a quadratic parent function and what are its characteristics? So we'll take a look to start with. The quadratic parent function is f of x equals x squared. So we'll take a look at an xy table to start with some ordered pairs. Some of these items and details you'll already be familiar with. So in the xy table you have points -2, 4 for example. -2 is the x, 4 is the y. You can see also f of x represents y. So -2, 4. It is the simplest function, by the way, this particular parent function, in the quadratic function family. And then you can also see some of the points start to uncover as we continue here. The graph of the function is a curve, as I said, called a parabola. As it turns out, these few points that you can see here, and these particular ordered pairs written as such, we have taken a look at in the past. We've worked with various graphing calculators. Please be familiar with how to graph both with and without a calculator. The vertex is the lowest or highest point on the graph of a quadratic function. In this particular case, 0, 0 is the lowest point. As it turns out, this parabola will open up, as we'll see here in a moment, as opposed to down. There's another ordered pair, just for good measure. And then we'll also take a look at, as we've discussed again in the past, things like the axis of symmetry. And yes, here's your parabola, of which it does open up. And you can see things taking shape that we've, again, taken a look at before. The parabola opens up. The vertex is 0, 0. It is also called the turning point of the graph. And this axis of symmetry, we call it, you can envision it actually as this imaginary line, so to speak, that cuts the parabola in half. It gives the parabola its symmetry. So every point that is on this half of the parabola, if you're to reflect it about the line, it lies on this half of the parabola. So if we continue, the axis of symmetry intersects the vertex and again divides the parabola in half. Let's move on. How does the value of the leading coefficient a affect the graph of f of x equals ax squared? So what we're going to take a look at here now is we're going to take a look at the idea that your parent function can be assessed and utilized in context, and here's how. Graph some functions of the form f of x equals ax squared with different positive a values on the same coordinate grid and compare them. So as you can see, and I'm going to be uncovering here all the graphs in context, but it says the graph of f of x equals 0.5x squared is wider than the graph of the function f of x equals 2x squared. And really, both of which we're going to be comparing to the parent function in red. So here's the functions. Okay, and yes, we'll be pointing to yet again more items in the graph or characteristics. So the red function, this is your parabola, represented by the parent function f of x equals 1x squared. Now everything we look at in terms of the green parabola and also the blue parabola will relate back to the parent function. Now the parent function is as simple as just, like I said, f of x equals 1x squared. There's nothing added, subtracted, multiplied, or divided to it. The green function is narrower than the red. It is being multiplied by 2. So it is actually a vertical stretch of the red. Imagine taking the red function and stretching it up. Therefore, this green is narrower than the red. And again, the a value, because it's equal to 2, that being greater than 1, that's the case. The blue function is actually wider than the red in comparison, because 0.5 is less than 1. So imagine a vertical compression or pushing down on the red function. The blue function would take shape accordingly. The vertex again is 0, 0 for all three graphs. And let's take a look at the connections further. For an absolute value of a, so the number in front of the function, x squared. If a is between 0 and 1 after the absolute value is taken, the shape of the parabola is wider than the parent function. Okay, so this blue function is pushed down vertically or compressed down vertically, but you can see the blue function is also wider than the red, the parent. For the absolute value of a greater than 1, the shape of the parabola is narrower than the parent. So as we described earlier, the green function is narrower than the red. Again, a vertical stretch is taking shape here. Again, the a value is greater than 1. How does the sign of a affect the graph of f of x equals ax squared? So graph two functions, again, of the form f of x equals ax squared with the opposite a values on the same coordinate grid and compare them. When a is greater than 0, the y-coordinate of the vertex is the minimum value of the function. When a is less than 0, it is the maximum. So here's a good example, certainly, of both that we'll take a look at. So the red function, okay, is obviously a parabola that opens up, while the blue function is a parabola that opens down. It does describe here, as I said here, similarly, or at least in the sense of what the blue function is doing here. F of x is equal to negative ax squared is a reflection of f of x equals ax squared over the x-axis. So a couple things again. The red function opens up. Again, it has a minimum point where the vertex is, while the blue function, of course, opens down. It has a maximum value where the vertex is. This statement, again, is speaking to the idea that we have, if you take the red function and flip it or reflect it about the x-axis, the blue function takes shape. Now this is happening again because if you look at the a value here, it's 1.5, here negative 1.5. So the functions look identical, of course, but one is reflected about the x-axis to give you what you see in blue. So those are the comparisons to be made. When a is greater than 0, the parabola opens up. When a is less than 0, the parabola opens down. Example 3. Interpret quadratic functions from tables. Over what intervals is f of x equals 4x squared increasing? Over what interval is it decreasing? Use the function to make a table of values. So we're going to actually be looking at, yet again, an xy table with x and y, but also the ordered pairs. When is it decreasing? When is it increasing? So there's one ordered pair. You can actually plug those in to see if they work. Negative 1, 4 is the next ordered pair, and so on and so forth. Turns out that the function values are decreasing, but only up until you reach 0, 0. It turns out that the vertex of 0, 0 is the turning point of the function where it changes from decreasing to increasing. So let's see now the change, 1, 4, and then up 2, 16. So now the function values are increasing. So y goes from going down to the left of the vertex or less than the vertex, y coordinate of 0, as you can see from 0 to the left. Okay, 0 to the left, these are all negatives, left of 0, but these are decreasing, while to the right of 0 or greater than 0, the y's are increasing. Turns out the function is decreasing over the interval x less than 0 and increasing over the interval x greater than 0. Now you could graph this. If you were to take the time to actually look at f of x equals 4x squared, your parabola does open up because it's a positive a value, and the vertex is at 0, 0 as it describes here. So here's a quick graph for us to take a look at. Again, to the left of the vertex, and I didn't make an xy axis, but I could do that. It turns out that this is the decreasing aspect of the function, left of the vertex, and this is the increasing aspect of the function. Again, given the vertex of 0, 0, what do the points do from there? Okay, moving on, example 4. Apply quadratic functions. The owner of a new dance studio is installing wooden floors in all of the dance rooms. How much should the owner expect to spend on flooring for a square room with 15 feet or foot side lengths? And it also describes here that it's $8.75 per square foot. Here are your dimensions. So if you take a look, I'm going to start the process by uncovering, writing a function that can be used to determine the cost of the flooring. Most word problems demand this, I would argue. You have to set yourself up for what's to come. So let's take a look. C of x will represent the price per foot squared of flooring times the area of the dance floor in feet squared. When you multiply price per foot squared times foot squared or feet squared, that ends up being price. The units cancel. In that respect, if you take a look, $8.75 times x squared, that in turn, knowing what x is, for example, will yield a price quantity. Find the value of the function when x equals 15. Certainly we can do that. So here's your function again. C of x equals 8.75x squared. Plug in 15 or substitute and you end up with 8.75 times 15 quantity squared, or $1,968.75. The cost for a new floor for a square dance floor with those particular side values of 15 feet each is $1,968.75. Example 5. How do the average rates of change for f of x equals this function and g of x equals that function over the interval from 2 to 4, so x is only in between those values, compare? So let's take a look. Step 1 is to graph the two functions. So they've done it for you here, so we'll take a look very briefly and quickly here how that takes shape. So you can see the blue function as y or g of x equals 1.5x squared. Yes, you could graph this as y equals that on your calculators. This, of course, is the other. So this is 0.75x squared. This a value of 1.5 versus this a value of 0.75, we can see the difference, hopefully, where the blue is narrower than the red. So it turns out we're going to continue finding the value of each function at the endpoints of the interval. In other words, remember, we're only doing this between 2 and 4. Again, the blue function, 2 and 4. So both red and blue, the ordered pairs are highlighted for 2 and 4 accordingly. So you can go to the f of x equals 0.75x squared function, plugging in 2, yielding 3. You can see that on the graph in red. You could do the same with 4. So 4, 12 there in red. And of course in blue, 2, 6, 4, 24. So we continue. Find the slope of the line that passes through each pair of points. So if we do that, doing the slope for the red function, the red curve, we do 12 minus 3. Again, the y's subtracted divided by the x's subtracted. We get 9/2 or 4.5. So the rate of change for that is 4.5. Well, the rate of change for the blue, same idea, 24 minus 6 divided by 4 minus 2, and you'll end up with 18/2 or 9. So this is the rate of change on the red function between those two ordered pairs in red, and then of course for the blue function, 4.5 versus 9. The rate of change for function g, as you can tell, is twice the rate of change for function f. So there is that connection that we need to make. And for the sake of the next step here, it says on average, the values of function f increase by 4.5 units, and the values of function g increase by 9 units for each increase in x over that interval between 2 to 4. How do the rates of change relate to the values of a in the functions? For positive intervals, the greater the value of a, the greater the average rate of change. In this case, the ratio of a values in the two functions is the same as the ratio of the average rate of change. So it turns out that we can establish, just by virtue of the a value, we can establish a commonality for future instances and how the graphs take shape. So pay attention to that and notice how the rates of change relate to the values of a.